switch to English mode. Okay, so so this is the algorithm for querying the segment tree. Okay, so you can see that. Okay, it's a very, very simple one. Okay, so given you know, the node V, okay, which is of course initially is a root of the segment tree, and the QX, which is the query point QX. Okay, we want to identify all the intervals that contain QX. Okay, so basically, okay, we first report all the intervals that stored at this node. Okay, you know, which is you know, supposedly, I mean, if you are at this node V, okay, you are supposed to you know, the interval contains in this, what should I say? Like, because you start from the root, right? When you start from the root, okay, when you start from root, you can think about this. The root, okay, will its associated interval is going to be the whole line, right? Will be the whole real line, okay, because it's a union of all the intervals of its subtrees, right? So basically the root, the corresponding interval for the root is going to be the whole real line. So no matter what the QX is, it must the corresponding interval of the root must include QX, right? So in case if a certain interval, you know, is associated with the root, that means that the interval actually include the whole real line, which should include QX as well. Okay. If not, okay, then we go down. Okay. I mean to is one of its children. I mean, which contain QX as its interval. Okay. So basically, you can see that. Okay, when you are I mean, when you are, I mean, in the query algorithm, the node V must, okay, starting from the beginning, must include QX as part of its associated interval. Okay, so that's okay. So it's going to, you know, report all the intervals, okay, associated with this node. So if V is not a leaf, so then you check if QX belongs to the left child, the interval of that child. If that's the case, you are going to, you know, call the query segment tree left child QX. Otherwise, okay, if it's not included in the left child, it must include the QX must be included in the right child. So you do, otherwise you do the query segment tree right child QX. So you can see that, okay, you know, each this report all the interval in IV basically is a part of the output. It's part of the output, right? So it's like that it belongs to that KV. Okay, and you have one comparison, right? You have to do one like constant time, like not comparison, but check if QX belongs to the left child of the interval of that child. So that's that you add one there. So it's at node V you spend like 1 plus KV time. Okay, and because I mean at each level you are only going to do you know do this once basically, like I mean, you know, so the total number of time this is going to be executed is going to be proportional to the height of the tree. So it's going to be this one times log n. So basically it's going to be, log n plus k, where k is the number of reported intervals. So this is like the query time, okay? And the construction of the segment tree, okay, is very interesting, okay? First, okay, you have all the elementary interval, okay? Say you already have those n intervals. So you have those 2n endpoints, okay? And you can create those elementary intervals in linear time, right? Okay? And with those linear time, like elementary interval, of course, you need to sort those 2n points from left to right, right? The sorting takes n log n amount of time, okay? But that will only be done once, okay? They will only be done once. And after that, it takes linear time to generate all those, what should I say, like 4n plus 1 elementary intervals. And remember, all these things will have to be associated to the leaf nodes, right? So pretty much like you have 4n plus 1 leaf nodes, okay? And so you first create this tree structure first, okay? And from the bottom to the top, you can create like the corresponding like a interval for each node, starting from the leaf node to the parent, to the parent's parent, and so on until to the root. So, well, the time to do this, again, is going to take linear time because like you have a linear number of internal nodes, right? Okay, so then after that, okay, we first get all this taken care of. Then we try to, okay, we first take care of this, all this structure, and then we start inserting this, for example, S1 has to be stored, this one, right? So we then start to decide where to put S1, where to put S2, and so on. Okay? Okay, so here, okay? So this is the algorithm to put to insert each interval, okay? So basically, okay, if the interval of V, okay, starting from the root, okay, if interval V is part of this interval, okay, then we store this interval at V. Okay, else we check the left child, the interval of left child, intersect this interval is empty or not. If it's empty, okay, then we don't need to go to the left child. Okay, but if it's not empty, we do the insert segment tree, left child, x point, this interval. Okay, and so also we check if the right child, the interval of the right child intersect with this interval is empty or not. If it's empty, we don't need to do anything. If it's not empty, then we go further to the right child. Okay, so we first check if we can put this interval at the node V, or if we can do that, then we don't need to do any of this. Because if the interval is stored at the parent, you don't need to store that at its children node anyway, right? So this is how we do it. So you can see that, okay, in the worst case, you are going to go down further, right? One level at a time. But remember, we already proved that at each level, it's not going to, you are not going to have more than 3 nodes to store that interval, right? The same interval. So in the worst case, okay, as I said, like you are going to end up having like this interval stored at 2 nodes at one level. Okay, so in the worst case, the insertion of one interval, the upper bound is log n. Okay, upper bound is log n. So because we have n intervals, right? So it's going to be n times log n. So the insertion of all these intervals take log n. And remember previously, the sorting takes n log n, right? And the construction of the binary tree, I mean, well, that one takes linear time. So the whole thing will take n log n. Okay? So a segment tree for a set I of n intervals uses n log n storage and it can be built in n log n time. And using the segment tree, we can report all intervals that contain a query point, okay, a particular query point, which is qx, by the way, in log n plus k time, okay, where k is the number of reported intervals. So this is like a conclusion of segment tree. Okay, so we actually, in this chapter, we talk about 3 different data structures, right? 3 different data structures. And, but we haven't finished this yet, okay? We need to go back to the windowing problem because we only talk about the segment tree and, I mean, for one-dimensional, right? But this is really not exactly the originally windowing problem that we are talking about, okay? So here, okay, let S be a set of arbitrary oriented disjoint segments in the plane, okay? We want to report the segments intersecting a vertical query segment, okay, Q, which is QX times, okay, QY prime. So it has like a, a certain X coordinate and the Y coordinate range, okay. Keep in mind, this represents one boundary, okay? To be exact, let's assume it is the left boundary of the query point, of the query window, okay? Left boundary of the query window, okay? So, we can build a segment tree T on the X intervals of the segments in S. Okay, a node V in T can be considered to correspond to the vertical slab INTV times this from this is like what should I say, like the infinite infinite range for the Y coordinates. Okay, so first we don't let's I'm sorry. Let's do not consider the Y range. Okay, we consider this negative interval to positive negative infinity to positive infinity. So a segment is in the canonical subset of V if it completely closes a slab corresponding to V. So we say that the segment spans the slab, but not the slab corresponding to the parent V. So we denote these subsets with SV, okay? So that's a segment corresponding to the node V. So to see what we are doing, okay, let's try to look at this figure, okay? So we will try to use the endpoints, okay, the endpoints. Actually, here we do not draw all the all the slab, okay? You know slab, right? Slab is like this, like a vertical region, okay? Infinite vertical region, okay? So each of these is called a slab, okay? So basically, like for all the endpoints, we try to consider its x coordinate, okay? It's kind of like you sort of project each of these segments onto the x axis。你投影这些，你把这些 segment 投影到你的 x 轴上。Okay, then each of these segments will become one interval, right? Right? And then you can create the segment tree like what we just discussed. Okay? So for example, okay, in this particular example, okay, if V1, okay, V2, V3, okay, V2 corresponds to this range, V3 corresponds to this range. And you can see because S2, S1, S2, you know, S1 is, where is S1? S1 is here. S2 is here. So it goes across the whole region of V1, V2, right? But not the parent, because parent V1, okay, corresponds to this bigger region, the union of these two regions. Okay, for V3, okay, store S4 and S6, because S4, okay, it goes across this region. S6, where is S6? Here. Go across this region. So you can see S4 and S6 are stored here. But at the parent node, okay, V1 is stored S3 because S3 go across both of these regions. Okay, so this is S3 is stored at the parent node V1. Okay, so you can see the concept that we use here is pretty much the same as the segment tree, right? Okay, but we didn't really draw the whole thing because if you draw the whole thing, obviously this thing needs to be extended. This thing needs to be extended, right? Okay, because we need to consider all the endpoints, right? Okay, here, I mean, we didn't draw everything out because you can see this is just part of the tree. There are some other part of the tree, but we didn't draw the whole tree. Okay, but you get idea, right? I hope you get idea. Shouldn't be difficult to see that, right? So the concept of breaking each of the, I mean, the whole two-dimensional space into a number of slabs. Okay, and you know, at this node, for example, V2. Okay, V2 store S1, S2, and the S1, S2, you can see S1, S2. Both S1, S2 go across this slab, right? And the same thing, S4 and S6 go across the slab represented by V3, right? S4 is here. S6 is here, right? Okay, so, okay, the segments in the canonical subset SV span the slab corresponding to V, okay? So that's exactly what I just talked about, okay? And that they do not intersect each other. Remember, I mean, previously we talked about disjoint segments, right? These segments are disjoint, right? So they do not intersect. So because they go across the whole slab and they do not intersect, so what does that mean? It means that this implies that the segments can be ordered vertically. It's something like this, right? So if say, if this slab, okay, if this slab is corresponding to one node, okay, then that node, okay, the SV is going to contain S1, S2, S3, S4, and S5, right? Okay, and because this S1, S2, S3, S4, and the S5, they are disjoint, they do not intersect. So they sort of, you know, partition, or probably let me not use partition. They sort of like divide this slab, you know, in it can be, you can treat it as there's an ordering, okay, from top to the bottom, right? From top to the bottom. So you can create a binary search tree for this. Okay, S3 is the middle one. S2 is, well, the middle of the top, okay? S5 is the middle of the bottom, and so on, okay? So this one allows you to quickly verify if a point inside the slab. This allows you to quickly verify if a point inside a slab is in which region. Is in maybe like is below S1, above S2, or like below S4 and above S5, something like that. You can do this very quickly. Okay.
Even this in our homework.
Huh? Yeah, this is part of homework. Yeah, so you can see that I actually put a lot of like you know. The reason I assigned that homework has a lot of reason for that. Okay? So if you have done your homework, you understand what I'm talking about, right? You can query like the whereabouts of a particular point inside this slab, like it is above a certain line and below a certain line very quickly. Okay? So okay, the total data structure for the set S is thus as follows. Okay, the set S is stored in the segment tree T based on the X interval of the segments. Okay. By the way, I mean, if before I talk about this, I probably should let me again remind you. Okay, if your segment, if at least one endpoint fall inside the window, we can use range tree to deal with that, right? So remember those 4 cases thing, right? The first 2 cases and the part of the 4th case can be dealt with by the range tree, okay? If at least one endpoint fall in the window, right? So here, okay, we are concentrating on the case where the segment there, whose endpoints, whose both endpoints are not in the window, inside the window. If any of the endpoints are is in the window, then we don't need to worry about that case, okay? So So here we can assume like all these segments, their endpoints are not inside the window. So as I said, one way to verify that is that, okay, maybe this segment will go, it will be intersect to, it must be intersect. It must intersect like at least one of the, actually 2, okay. I mean 2 boundaries of the window, right? So no matter how you draw the window, okay? Say, this is a window. If both of your endpoints are not in the window, then it's something like that, right? Or it could be, well, maybe something like this. Okay, or like this. Right? So it must intersect with the boundary twice. Right? So here, okay, we just pick one boundary as an example. Okay, we pick one boundary, which is this one. We pick this boundary as an example. Okay, and the same idea can be applied to the other boundary. Okay, but and it will not increase the complexity anyway. Okay, so we will just focus on the left side of the left boundary of the query window. Okay. Okay. So we first, okay, we store these segments, okay, based on the x interval of the segments, okay, in a segment tree. We know we can do that, right? Okay, we know how to do that, and the complexity is not that expensive. And the canonical subset of a node V in a tree, in a segment tree, which contain the segment spanning the slab corresponding to V, but not the slab corresponding to the parent of V. Okay, it's, the segment is stored at the highest node that spans that slab, right? Okay, so based on the vertical order of the segments within the slab, so we can, this TV, this SV, we can, for those segments, okay, for these segments, we store them in a binary search tree, TV, okay, based on the vertical order of the segments within the slab. Okay, so it's going to be something like this. This is the TV. Okay, if the V has like this 5 segment that go across this slab, then we store them in the binary search tree like this. Okay, and then how do we do? Okay, we search with QX in the segment tree in the usual way. Okay, and at every node V on the search path, we search with the upper and the lower endpoint of Q in TV to report the segments in SV intersected by Q. Okay, so remember the Q actually stands for, the Q stands for this one. This is the Q. This left boundary is the Q. Okay? And the x coordinate value of Q is Qx. And the y coordinate value of Q is the where is it? Here. We search with upper and lower endpoint Q. Okay, so we search these 2 endpoints. So it's kind of like say we already know, okay, this lab contains QX. Okay, but we need to know like if this segment go across that boundary, then say that boundary is here. So it has a range, right? It has a range. It has a wide range, right? So we need to check, we need to search on the endpoint. For example, for the upper endpoint, it's in between S2 and S1. For lower endpoint, it's in between S4 and S5. So based on that, we know S2, S3, S4 are intersected with our segment Q, right? So we can safely report those segments as, the segments that, what should I say, at least part of those segments will be in our window, right? Okay, so this basically is a one-dimensional range query. Okay, the search in the TV takes log n plus kv time, where kv is the number of reported segments at V. So this is very easy, very easy. Okay, and then, okay, final remark. Okay, that S be a set of n disjoint segments in a plane. The segments intersecting a vertical query segment can be reported in big O log n squared plus k time with a data structure that uses n log n storage, where k is number of reported segments. The structure can be built in n log n time. Okay, so this is we talk about the vertical query segment, right? The Q. Okay? The reason for the log n squared is because, okay, we need log n to find all the slab that contain Qx. And we need another log n to query the, which segment actually is in the range of y. Okay, so it's like log n times log n. Okay, so this is like a kind of like a this is the reason why we have a log n squared. And then, okay, so this is for one vertical query segment, right? So that has to be a set of n segments in a plane with disjoint interiors. Okay, so now we are in a position to talk about to answer the window query. Okay, the segment intersecting an axis parallel rectangular query window can be reported in big O log n squared plus k time with a data structure that uses n log n storage, where k is the number of reported segment, and the structure can be built in n log n time. So here, okay, what do we need to do? First, we need to find out the segments whose at least one endpoint is in the window by using the range tree. Okay, by using the range tree. After that, okay, for the rest of the segment that spans the whole window, okay, such that the endpoint are not in the window, we need to use like the segment tree. Okay, we need to use the segment tree to for example, we do the segment tree on the left side. We do the segment tree. We can do the similar thing on the right side. We can do the similar thing on the top like a boundary and the bottom boundary. So you sort of do this thing for 4 times. Actually, you can do 3 times because, well, yeah, 3 times should be enough. Because if one segment, spans the whole window, what should I say? Like it must go across at least 2 boundaries, right? So something like that. Okay. Yes.
The time complexity of log n squared plus k is caused by the range tree, right?
You mean this one?
No.
This one? This one. Okay. This one. Okay. You need log n to find a slab that contains Qx, right? Yeah. I mean. Yeah. You need log n to find all the slab that contain Qx, right? And then you need another log n to find like which segments are will be intersecting with that because you need to search on the 2 endpoints, right? Yeah, that's another range query. Yes. So yeah. So this is, so even though we need to do like this segment tree multiple times, but the complexity does not add up to exceed the current complexity. It's because we are going to do this constant number of times anyway. Okay, so that this is fine. Okay, and keep in mind that this is the most difficult situation. What do I mean? It's like where we consider the situation where the segments can be at arbitrary orientation. Okay, if the segments are parallel, axis parallel, then at least the query type can be reduced to log n plus k. Okay. So there's a slight difference but of course not that much. Okay? So any question? We are finally done with this chapter, okay? I mean, it's a long chapter, okay? It takes, much more time than I expected. But we have like 5 more minutes left. Do we? Okay. Just as a starter, I will start the next chapter, and just to motivate what we are going to talk about. Probably not. We're not going to talk too much anyway. Okay. So the next chapter that we are going to discuss is called binary space partitions. Okay. The algorithm that we are going to cover is called the Painter's algorithm. Okay. Just look at the name of the algorithm. It looks so artistic, but it's not like that. In reality, the application of this is more related to game playing. Okay. So we know, like, for example, in a flight simulation visualization, when you are, in a computer simulation where you are, controlling the airplane, the screen needs to display a lot of objects, right? But depending on the viewpoint, okay, some object has to be occluded, right? Some object has to be because of the occlusion, some objects shouldn't be seen, right? You should see, for example, like, this building, but you cannot see the building, anything behind that building, right? So because that building blocked your view, right? So in other words, this problem is called hidden surface removal. We need to determine for each pixel on the screen the object that is visible at that pixel. And that pixel, as I said, that's a viewpoint. It could be arbitrary. Okay, when you fly the airplane, like the viewpoint can be arbitrary. This similar concept appear very common in game playing. A lot of people like to play. I don't know what's that called. Like you control a gun and keep killing people. Not people, zombies. Huh? Yeah, you just kill, yeah, a lot of those games. Okay. But anyway, obviously, normally when you play those games, you are in a maze, right? Dungeon, maze, right? 地下城迷宫，对不对? Okay, you are in a dungeon, maze. A lot of times, you cannot see some object. You have to change viewpoint in order to see certain object, because maybe the wall will block certain objects from your screen, right? So the same concept, okay, will be applied, okay? So that's basically called hidden surface removal. So basically, this concept has a lot of application in game playing, okay? And to do these shading calculations, it takes a lot of time, okay? It takes a lot of time. And in traditional algorithm, okay, use what we call the Z buffer algorithm, okay? The Z buffer is like it store each pixel the Z coordinate, okay? So it treat it as like 3-dimensional, okay? So you use the Z coordinate of the current visible object. So there's an advantage of doing this approach, okay, which is it can be implemented in hardware. So if your hardware support the Z buffer, which, to be honest, a lot of like video, the video card, okay, hardware support the Z buffer. Probably you don't talk about this technique anymore, okay? Because back to like when I was like in graduate school, okay, like 20 years ago, okay, if a video card supports Z buffer, okay, that's a selling point. Let me put it this way, okay, and it will be written on the box, okay. But now because the Z buffer is considered the everybody support it, okay. You know what is the biggest driving force of computer hardware? It's gaming industry. Okay, so you can see that like a video game, because of a lot of video games, like the video card, you see Nvidia, those companies, they create like the video card to be so powerful, so sophisticated. Okay, so this even though this Z buffer can be implemented in hardware, but it requires a lot of extra storage space. Okay, so in this chapter we are going to use something called the Pentas algorithm. Okay, which is able to avoid those extra costs. Okay, and we are able to deal with what we call hidden surface removal. Okay, in this chapter, but I guess it's about time. So we will stop here. Okay, next time we'll start from this problem. Okay, we'll talk about this problem next time. I think I will be able to finish this chapter next time. So next week, okay, instead of this week, next week I'm going to give you homework 5. Okay, homework 5. Not this week, but next week. Okay, will be okay? Okay, so I guess that's it for today. Any question? Yeah, to be honest with you, it seems to be we are the only class at our department which stays in-class teaching, it seems like I just asked the department, except very few classes, almost I wouldn't say 90%, but at least 80% of the classes in our department are now online. Okay, so that's why if you go out, you don't see many students around. That's because almost all classes become online. But do you guys feel like we continue this way is better, or you guys prefer to switch to online? For me, of course I prefer in-class teaching, but I kind of feel like because it has become probably a concern for many students, because considering the number of infections every day now is over 50,000, right? So are you guys comfortable with the in-class teaching or not?
Teacher, I personally feel real-time online teaching is fine, but if it's just a recorded video, I think that will be.
Of course, if we switch to online, it's going to be online. Real-time online. But even for real-time online, I have to admit, okay, from my previous experience, it's not so easy for me to take questions so promptly. You know what I'm saying? Okay, because normally, in a web CT or like a Zoom, the student normally only asks questions through a chat room. Okay, by typing. So normally, I don't pay attention to the new message in the chat room so frequently. Let me put it this way. It's not like I ignore the question. It's just I sometimes do not check it so often.
We open the microphone and just talk.
That's probably not a good idea because then it's, my previous experience is that if student turn on the microphone, there will be a lot of noise, not by you guys, but by the background noise. Okay, so normally we shut down the student's microphone. Okay, because of that. So that's another reason I prefer in-class teaching. But if you got, let me put it this way, okay. If you have concern with this, okay, if some of you prefer online teaching, okay, I mean, which will still be real time, but if you guys are feeling more comfortable with that, let me know by email, okay. If I see enough number of requests, I may switch to online. Let me put it this way. Okay, I know if I ask you, because first, I mean, not many students show up, right? Second, even if I ask you, have you guys, no, probably nobody raised hands, just I mean, a lot of questions I ask, nobody really give me opinion, face to face, but maybe you guys can write me email if you feel switch to online, help your learning, will make you feel more comfortable with with this class. Let me know. Okay? Okay. So I guess that's it for today. Okay. Thank you.